Today in physics, we'll be talking about the Atwood machine under the effects of friction. This is part 1. So we have this model of an Atwood machine. We have a square prism, A, B, C, D, so it's actually a three-dimensional object. We're just looking at from the front. And on A, B, C, D, we have two massless objects, namely P and Q. And P and Q are always touching the square prism A, B, C, D. In between P and Q, we have a string S1, and to the left of P, we have S0. To the right of Q, we have S2. And these three strings are all massless strings, and they're also inextensible, which is to say that their length never changes, so they can't be stretched or compressed together. And we also say that there is static friction between P and the face that it's on, namely AB, and however width or height that ABCD keeps on going. And same thing with Q. So which is to say that on the face of ABCD, we always have static friction that's also taking place. Now we have a question. And the question is thus. We have a tension in string S0. We'll call it T0. So S0 has a tension of T0. And we're asked to find T1, which is the minimum tension in string S1. So T1 is on the string S1 in order to keep P at rest. Okay, we're asked to find what T1 is equal to. Now we might be tempted to say that T0 must be equal to T1 since the strings are connected and P is massless. However, we do have friction, and so once we have friction is going to somewhat help T1 in balancing out T0. So we find that T1 and T0 are not necessarily the same. So let's draw a force free body diagram on P to see how we can keep P at rest. So here is P, and T1, this is T1. And we can decompose T1 into two components. One component that is parallel to AB, and one component that is perpendicular to AB. So if we draw as such. So this is the component parallel. This is T1. Here's our angle. Our angle is given to be pi over 4. So this is T1 times cosine of pi over 4, and this is T1 sine of pi over 4. Now we also have the force T0, so here is T0, and T0 we can also split it into two components similar to T1, and our angle once again is pi over 4, so the component parallel is T0 cosine of pi over 4, and the component perpendicular to AB is T0 sine of pi over 4. We also have another force. If we only had T1 and T0, then we can sort of see that it seems like that P would slide downwards toward A rather than towards B, sort of following the direction of T0. So we have friction, and friction is going to work against that. So it works along parallel to AB, and it works upward. So this is our force of friction. And the force of friction is given by the coefficient of friction, which we are given to be mu0 times the normal force. Times the normal force Fn, which is acting on P, which we haven't drawn here, but we can add it now. So this is our normal force, Fn, and that is perpendicular to the surface AB. Now, when we're trying to find Fn, we want to see which forces are causing P to press down on the surface AB. Once it presses down, then the surface AB will in return give P the normal force. So we say, all right, Fn is equal to, and here we see that the forces, the components of the forces T0 and T1 that are perpendicular to AB are pushing down on that surface. So that's the sum of those, namely the sum of T0 sine of pi over 4 and T1 sine of pi over 4. The sum of those will equal to the normal force given from the surface AB to P. So we say Fn is equal to T0 times sine of pi over 4 plus T1 times sine of pi over 4. Let me write these pi's again. So the two tensions have components that are perpendicular to AB. When we add those together, we get a normal force. So we can conclude that the friction force must be equal to mu 0 times the normal force, which we know to be T0 sine of pi over 4 plus T1 sine of pi over 4. Now we still want to find T1, so we can see that the components of the forces T0 and T1 that are parallel to the surface AB will cause an acceleration to P to either go downwards on the slope of AB or upwards on the slope of AB. And since we want P to remain at rest, that means the forces acting on P in the parallel direction must be equivalent for opposite sides. So we have T0 times cosine of pi over 4. That's a force that's acting downwards. It must be equal to the tension force, T1 cosine of pi over 4, that is acting upwards. But this T1, the tension force, is also helped by friction in moving upwards, as we can see. So we add the force of friction. So now we want to solve for T1. So we can plug in what we got the force of friction to be, so that we get T0 times cosine of pi over 4 is equal to T1 times cosine pi over 4 plus the force of friction, which we got in our step here above, namely mu 0 times T0 sine of pi over 4 plus T1 sine of pi over 4. Now that we have this equation, we know what T0 is, that was given. We know what mu 0 is, that was also given, and we have all our angles already. So all that remains to do is to solve for T1. So let's move the T0s next to each other. So T0 cosine pi over 4 minus mu 0 times T0 sine of pi over 4 is equal to T1 times cosine of pi over 4 plus mu 0 times T1 sine of pi over 4. So on the left side we can factor out T0, on the right side we can factor out T1 to get T0 times cosine of pi over 4 minus mu 0 sine of pi over 4 is equivalent to T1 times also cosine pi over 4, but this time we're adding mu 0 sine of pi over 4. So we can conclude, therefore, that T1 must be equal to T0, and if we divide the coefficient of T1 on both sides, we get T0 times the cosine of pi over 4 minus mu 0 times sine of pi over 4 over cosine of pi over 4 plus mu 0 times sine of pi over 4. So that's our answer for T1, the minimum tension in string 1, which was between bodies P and Q.